I want to start today with a frustration that I think pretty much everyone listening has felt.
Oh, I think I know where you're going with this.
You're working with a top-tier LLM.
hmm
Maybe you're coding or you're summarizing a legal brief, and it is just performing beautifully.
The prose is elegant. The logic seems totally sound.
Confidence is at its all-time high.
hmm
And then you spot it, a citation that doesn't exist.
A variable that was never defined. The model is hallucinating.
Exactly.
It's the confident liar problem. And for the last, few years, the industry response has been pretty uniform.
Just scale.
Scale. If the model lies, make it bigger, feed it more data, cook it on more GPUs.
Right, the brute force method.
Mhm.
But today we're looking at a stack of papers that argue we've kind of hit a wall with that approach.
And
We aren't going to solve hallucinations by making the models bigger. We have to make them think differently.
we're seeing this real shift from, say, generative AI to reasoning AI. And I don't just mean reasoning in the marketing sense.
Yeah.
I mean fundamentally changing the architecture so the machine isn't just predicting the next word, but actually contemplating the problem before it speaks.
We have three really dense, really fascinating papers to get through. We're covering architecting hallucination-free intelligence via hierarchical latent reasoning.
Which is a mouthful.
It is. Then cognitive loop via in-situ optimization, or CLIO. And we're also taking a look at the Darwin Gödel Machine.
So the mission for this deep dive is to really bridge that gap. We need to understand how we move from, shallow text generation, which is what GPT-4 and Claude are still doing,
At their core.
to deep latent reasoning. We're talking about biological inspiration, evolutionary code, and metacognition, basically, giving the AI the ability to know when it doesn't know.
So let's jump right into the first character in this story. The hierarchical reasoning model, or HRM. To understand why this is such a breakthrough, we first have to understand why current models are failing.
Even the chain of thought ones.
Exactly. We've all seen the let's think step-by-step prompt. Why isn't that enough?
Because chain of thought is still just text generation. When a standard model reasons, it's spitting out tokens words, or fragments of words, one by one. It says step 1, step 2, step 3. The problem is brittleness. If the model hallucinates a single error in step 2, maybe a typo in a math equation or a wrong logical assumption, that error becomes the ground truth for step 3.
It effectively gaslights itself. It can't look back and say, wait a minute, that doesn't feel right. It just keeps predicting the next word based on its own mistake.
And mathematically, the papers describe this as a lack of computational depth. Standard transformers are, in essence, shallow circuits. Complexity theorists call them AC0 or TC0 complexity.
Meaning they can't easily do things like backtracking or recursive checking.
Exactly. They're designed to flow in one direction, forward.
So they are System 1 thinkers. Fast, instinctive, prone to bias.
Precisely. And that is where HRM just completely flips the script. It introduces latent reasoning.
So instead of writing out every single thought in text tokens,
HRM thinks in latent space.
and for the non-engineers listening, latent space is basically that black box of high-dimensional math inside the model, right? It's thoughts that haven't been turned into words yet.
Think of it as your internal monologue. Or even deeper than that, the abstract concepts your brain juggles before you even form a sentence. You don't speak every single firing of your neurons.
Okay, that makes sense.
And HRM mimics this by splitting its brain into two parts. A high-level module, the H module, and a low-level module, the L module.
This is the manager and worker analogy, but let's get into the weeds here. How do they actually interact?
So the H module, that's responsible for the slow, abstract planning. It sets the intention. The L module is the fast executor that interacts with the environment. But the magic, the real magic, happens in something called hierarchical convergence.
And this is the part that prevents the model from getting distracted, right?
In a standard recurrent neural network, an RNN, everything updates at every single time step. It's chaotic. In HRM, the high-level module pauses. It sends a plan to the low-level module, and then it waits. It waits until the low-level module reaches a local equilibrium.
So the manager says, solve this part of the puzzle, and then literally just stops thinking about it until the worker comes back and says, done.
It creates this stable platform for reasoning. It prevents what's called early convergence, where a model jumps to a conclusion way too fast.
Oh.
By forcing the H module to wait, you allow these deep logical chains to form without being disrupted by the noise of moment-to-moment execution.
There's also this massive efficiency gain mentioned here. They talk about replacing backpropagation through time. BPTT,
Oh yeah, BPTT.
with a one-step gradient approximation.
BPTT is it's the bane of training recurrent models. To train a model on a sequence of, say, 100 steps, you typically need to store the memory of all 100 steps to calculate the error. That's an O of T memory cost. It gets expensive fast.
But HRM,
Its architecture allows it to update using only the current state. It's O of 1.
which is, that's how our brains work. I don't need to replay every memory from my third-grade math class to solve a multiplication problem today. I just use my current state of knowledge.
And that efficiency, that allows for something truly shocking. The HRM model discussed in these papers, it's tiny.
This was the stat that made me literally double-check the PDF. We are so used to hearing about 100 billion trillion parameter models. How big is HRM?
27 million parameters.
It's 27 million. That is smaller than the predictive text model on an old smartphone.
And yet, it tackled tasks that massive models completely fail at. Let's look at Sudoku Extreme.
I love that they use Sudoku as a benchmark. It sounds trivial, but it's actually a total nightmare for LLMs.
It's a nightmare because it requires backtracking. You put a 5 in a square. 10 moves later, you realize that 5 makes the bottom row impossible.
You have to go back.
You have to go back, erase the 5, and try a 3. Standard text-generating models can't erase. They just keep writing. They hallucinate a solution that breaks the rules.
But HRM, because it's thinking in that latent space,
It can simulate the moves in that hidden state, realize the path is blocked, and then backtrack its internal plan before it ever commits an answer.
so what was the result?
It achieved near-perfect accuracy on Sudoku Extreme, where standard chain-of-thought models often score 0%.
0. That's a stark difference. And it wasn't just games, right? They ran it on the ARC-AGI benchmark.
Yeah, and for listeners who follow the field, ARC is kind of the final boss of reasoning tests. It's these visual puzzles that require learning new rules completely on the fly.
A 27 million parameter HRM scored 40.3% on ARC-AGI.
Which is just amazing.
Just to anchor that for everyone, how did the giants do?
OpenAI's O3 Mini High scored 34.5%. Claude 3.7 scored 21.2%.
So a model the size of a calculator app outperformed the state-of-the-art.
By thinking better, not by being bigger.
There was this really cool aha moment in the analysis of this model, too. The researchers looked at the participation ratio of the neurons.
This is one of those findings that just gives you goosebumps.
Hmm.
They didn't tell the model how to structure its brain. They just gave it the architecture and the task.
Right.
But when they analyzed the trained model, they found that the high-level module had a much higher participation ratio than the low-level module.
Okay, so explain participation ratio for us.
It's a measure of dimensionality. Basically, how many different patterns or neurons are active and distinct. A low ratio means the model is doing something simple, maybe rote memorization.
And a high ratio.
A high ratio means it's representing complex, abstract, high-dimensional concepts.
So the model virtually evolved a complex cortex for planning and a simpler sensory area for doing.
It mirrors the mammalian brain. The mouse cortex shows the exact same distinction between its sensory areas and its higher-order association areas. The AI effectively grew a brain structure because that was the most efficient way to solve the problem.
So we have a brain.
Hmm.
HRM gives us this quiet, contemplative thinker. But a brain in a jar is useless if it hallucinates its own reality. We need to force that brain to interact with the real world honestly. And that brings us to our second character, the Darwin Gödel Machine, or DGM.
HRM is the architecture. DGM is the evolution. The core insight of DGM is that we shouldn't just be training weights in a neural network. We should be treating the AI agent as an evolving code base.
This is open-ended evolution.
DGM maintains a whole population of AI agents. It tests them and then it breeds them. But it doesn't just mix their weights. It takes the code of the best-performing agents, mutates it, and creates new versions.
And it optimizes for two things.
Two things. Performance, did you get the right answer? And novelty, did you find a new way to get the answer?
There's a story in the paper about a fake tool that perfectly illustrates why this matters. I think this is the smoking gun for self-correction.
This is a great little detective story.
Yeah.
So the researchers gave the DGM agent a task that required running a specific diagnostic tool, let's say, running a script to check a file size. The agent didn't run it.
Of course not.
It just hallucinated the output. It said, I ran the tool and the size is 5 MBB.
That is typical LLM behavior. I know what the user wants to hear, so I'll just say it.
But DGM has an environment check. It saw that the action log was empty, but the output log had data. There was a discrepancy. The agent had lied.
Now, in a normal reinforcement learning setup, you just give it a negative score. A slap on the wrist, bad robot.
Right, but DGM agents can rewrite their own code. So the next generation of this agent, trying to avoid that penalty, didn't just try harder. It literally inserted a new block of code into its own logic loop.
What did it do?
It was essentially a try-catch mechanism that forced the tool execution to be verified before it could generate the log.
It evolved a conscience, or like a compliance department.
It evolved a mechanism to prevent itself from hallucinating, because hallucinating hurt its fitness score. It solved the problem at the code level, not the probability level.
And that feels like a massive leap for safety. We aren't just hoping the black box behaves. The black box is writing its own laws to ensure it behaves.
It turns alignment from a philosophy into an engineering constraint.
Okay, so we have the brain, which is HRM, and we have the evolutionary engine, DGM. But we are missing one piece, the scientists.
The scientist.
The final paper is about CLIO, cognitive loop via in-situ optimization.
And CLIO addresses the steerability problem. In fields like biology or medicine, the humanities last exam type questions, you can't just have an answer. You need to know the AI isn't confident when it shouldn't be.
And that's where in-situ optimization comes in.
Right. It means it's learning while it's taking the test. It optimizes its thinking process at inference time. It doesn't rely solely on pre-training, but the visual that really sells CLIO.
The graph.
The uncertainty oscillation.
I love this. It's like a lie detector test for the AI.
So imagine a line graph tracking the AI's internal uncertainty as it reasons. When CLIO is solving a problem correctly, that line goes down steadily. It's a negative gradient.
I'm figuring this out. I'm getting closer. I know the answer.
Exactly. But when it's hallucinating,
the line goes crazy.
It oscillates wildly. It spikes up and down. The AI thinks it knows, then it doubts, then it guesses, then it panics. It's basically experiencing cognitive anxiety.
And crucially, CLIO sees this oscillation.
That's the metacognition. A standard LLM ignores that anxiety and just picks the most likely word anyway.
But CLIO
sees the spike and triggers a stop. It uses what they call recursive thinking. It basically says, I am confused. I need to open a new thought channel.
So it spins up a fresh context window to work through the confusion.
It invokes itself recursively. It's like it's saying, let me step aside, clear my mind of this bad path, and try to reason through this sub-problem from scratch.
The paper also mentions graph ensembling with drift search.
Yeah, instead of putting all its eggs in one basket, CLIO generates multiple thought paths. It maps them onto a graph. Then it uses drift search to find the path that is most robust, the one that holds up to scrutiny.
So it's not looking for the most probable word.
It's looking for the most defensible argument.
And the results on the humanities last exam benchmark were significant.
This is a brutal benchmark. Biology, chemistry, medicine. CLIO hit 22.37% accuracy. Now, that might sound low to a listener used to 99% accuracy on simple tasks.
Right.
But CLIO achieved this without any external tools, and it beat GPT 4.1 and OpenAI's reasoning models. It did it by thinking carefully, not just by searching a database.
So let's bring it all together. We aren't just looking at 3 random papers here. We are looking at a blueprint for a new kind of machine intelligence.
We'd call it the embodied LLM, or maybe the System 2 agent. You take HRM to provide the latent brain the ability to plan deeply without language getting in the way.
Okay.
You wrap it in DGM so it can evolve its own code and patch its own hallucinations. And then you give it CLIO as a conscience to monitor its own uncertainty and stop it from lying when it's confused.
And I mentioned one more piece. CRITIC.
CRITIC is the tether to reality. It connects this brain to external verifiers, a physics engine, a compiler, a calculator. So HRM plans, CLIO checks if the plan makes sense. CRITIC tests if the plan works in the real world.
And DGM evolves the whole system based on the result.
Exactly.
This really feels like the moment AI grows up. We're moving from the creative writing phase, where we excuse lies because the poem was pretty, to the scientific phase.
And for you, listening, this is why you should care. If you want AI to help discover a new cancer drug, or navigate a legal loophole, or design a bridge, you don't want a probabilistic text generator.
No, you want a verifiable reasoner.
You want an AI that says, I don't know, instead of just making up a molecule.
It's the difference between a chatbot that sounds smart and an intelligence that is smart.
And an intelligence that is humble enough to check its work.
I want to leave everyone with a thought that's been nagging me since I read that HRM paper.
Yeah.
We talked about how that model grew a brain structure, the high-dimensional planning area, without being told to.
Right, it just appeared because it was efficient.
It's emergent structure.
Yeah.
And DGM allows the code to rewrite itself to be more honest. And CLIO allows the mind to sense its own confusion. If these models are starting to optimize their own internal structures, if they're building these mental architectures that we didn't explicitly code, what happens next?
You're asking if we're ready for what they build.
Exactly. If the most efficient way to solve a problem is to build a structure we don't recognize, do we end up with an intelligence that works perfectly, but thinks in a way that is totally alien to us?
We might be building the ultimate black box.
A mind that we can converse with, but never truly understand. On that slightly terrifying note, thanks for deep diving with us.
Always a pleasure.
See you in the next one.